Today, myself, Nikhilesh, and Sneha would be conducting the sessions. Before we get started with neural networks, let's revise some of the concepts that we have covered in last two sessions. So, the two major topics that we covered were rule-based approaches and machine learning based. So, the differences between them, and along with that, different types of machine learning like classification, regression, clustering, sequence prediction, and style transfer. So, to just recap quickly, a rule-based approach works based on a set of rules for a given data to get an output. But when it comes to machine learning, it works more of the model tries to learn the rules from the data. So it is both the approaches are little different and they have their own specific purposes, and we have went into detail in the previous session. So, and the second topic that we discussed were classification. So the classification is based on classes. So if you have a set of finite number of labels that you want to classify, like cat or dog, that's when we will use classification. And if we use regression, only if we have some kind of range between numerical values like A to B, like time, speed, velocity, or these kind of things, like any range values. And clustering, it is grouping of different clusters uh, based on the features that they have in similar, which are in similar. And next is sequence prediction. Like we discussed earlier, that the keyboard, the normal keyboard that we see in our phones, where we type few letters and we scribble few letters and we get the exact word. So based on the letters, you will be predicting the next letter or next word. So that is one of the example for sequence prediction. And fifth is style transfer. So like cloning the voice or cloning images style by using these kind of algorithms. So we have covered five, and now we'll get into neural networks. So let's get into the session. And so a lot of places you might have heard that neural networks are doing a lot better nowadays. So some of the reasons behind uh, it is group of smaller models put together. So that is why it works really good, and it is really easy to train these models. So, and we'll get into that, get into the depth into each and every part of neural networks in this entire slides. So before we get into the visualizations of how neural networks be, let's first check out this video.
Hi, I'm Nat.
And I'm Lo. And this is our 20% project, where we go find out about different Google stuff we're curious about.
Last year, we got to make a documentary about how voice search works. And that was the first time we heard about something called machine learning.
Since then, we've been kind of fascinated by it.
So today we're talking with Greg and Chris to learn more about it. How would you describe machine learning to someone?
Well, there's a lot of problems that's really easy to solve with computers. Computers can go and simulate how galaxies move and how the courses of asteroids going and how close they're going to come to Earth. I could never hope to go and do that, but I can go and do this problem like recognizing that that's a tree, which is so much tremendously more difficult for a computer.
It doesn't feel like intelligence to us because it's so effortless as a human being to do it. But for a computer, it's actually really hard.
Because the real world is kind of messy and unpredictable at times. The strict logical rules that go into traditional programming just don't work.
Instead of going and writing programs that solve the problem, we write programs that learn to solve the problem from examples.
And it's this process of learning that allows them to improve over time and to actually be more clever than they would be if we wrote down a very rigid set of instructions for them to follow.
Machine learning is in so many different things that we use today that it's kind of like this invisible magic ingredient.
Phones with the ability to understand human speech.
Machine translation, email spam filters.
When you go to the ATM and you give a check and it can read the handwriting.
Or a Photos app that can automatically organize your photos based on the things that you like to take photos of. Like, here are all my mountain photos, here are all my food photos,
Here are all my dog photos.
here are all my feet photos.
Everything from facial recognition to going and trying to recognize whether a particle is present in a particular collision at the LHC.
Which we just like to take a time out to say is that big tube in the ground over in Europe that smashes particles together at really fast speeds so that scientists can use that information to unlock the mysteries of the universe, among other cool things. Now back to our episode, because I am getting really dizzy doing this.
So researchers and scientists are still experimenting and trying to find the best ways to teach computers how to learn. But a lot of the progress is coming from these algorithms that are based roughly on how the human brain works, and these are called artificial neural networks.
So an artificial neural network is something that it's a rough mathematical cartoon of how a biological neural network works. In a biological brain, we have individual cells called neurons. Each neuron looks at what its neighbors has to say and then decide what it wants to say. And in artificial neural networks, we have little mathematical functions. We put them in some organized structure, and then we say, okay, you guys all together, learn to do this task.
We have lots of neural nets that are really great at going and recognizing, this is a cat, this is a dog, this is a frog, this is a mouse, this is a horse, this is a truck, and things like that.
So take, for example, trying to recognize what this is.
So it used to be that we were really proud if we could get a neural net with 3 layers to work. And it's recently that we've made a lot of progress on techniques that allow us to train much deeper neural nets.
And that's why this kind of machine learning is also called deep learning. A neuron in the bottom layer is just going to be looking at a tiny piece of the picture and making some computations about it. It doesn't understand anything about dogs specifically.
But what the neuron does understand is it says, I'm giving a signal that's useful for somebody who's giving a signal, who's giving a signal, who's giving a signal, who's giving a signal.
They're kind of able to unfurl this really high dimensional knot and pull it apart and make it easier to go and separate different things that are close together on the surface from things that were tangled all together earlier.
But then at the top, we'll put 2 neurons, and these neurons look at the whole picture so far.
They're basically experts at making the final call, figuring out, oh, all the layers below me said these things, so I know that this is a dog, or at least I'm 92.4% sure that it's a dog, so it's basically a dog.
And while there's been a whole lot of progress with teaching computers to learn, they're still much slower learners than we are, and they make mistakes that you and I wouldn't.
So what I was working on is sort of trying to find a way to go and look at a neural net and ask, what does the neural net think the platonic ideal of a cat is, or the platonic ideal of a dog, or anything it can classify as? And suddenly you can go and ask, neural net, what do you think a cat looks like? And you get a picture of a cat, or, neural net, what do you think a barbell looks like? These weights. And it goes and it shows you a picture not only of a barbell, but of an arm attached to a barbell. So the model thought that the arms, it only learned what barbells were from looking at pictures of barbells, and they're often held by muscular weightlifters. And so it learned that there was, barbells have arms attached to them.
It takes them a long time to learn. You show it a picture of a school bus when it's early in learning. The very next time you show it a picture of a school bus, it's only a little bit more likely to say school bus. It doesn't get it, even though that was the very last thing it saw. Whereas, you say to a kid, that's a filing cabinet. And then a second later you say, what's that? He's not going to be like, shoe, right?
Well, the more you describe this, the more I'm amazed by human beings.
Yeah.
The effect is like, wow, human beings are really amazing.
We're really amazing learning machines.
So you probably heard about a word called ANN, or artificial neural networks. So when we talk about neural networks, we have something called neurons in our head. So these neurons interconnect and they form complex network. So when we try to simulate that kind of network, that is called artificial neural networks. So this is how they look. So for a person who have no idea about what's happening, these are the images that the model gets to learn first before kind of predicting what they are. In this example, we can see cat and dog, and these are the neural networks. Okay, so all these connections, they are activated layers. So we'll get into activation layer and other stuff, but first let's see the input layer and output layer. So the input layer is taking the image of all the pixels. So when we look at the 1 minute, so when we look into the image, we can see that it is divided into some pixels, right? So these pixels gets gets into a row and they just pass through the network, and finally you get to have, you're gonna go to cat and dog. You're gonna find out the predicted output by sending the image into this neural network. We'll get into what happens inside this network in future slides. But as of now, you have the input layer and some hidden layers and an output. So these networks can, these can get as complex as possible to even classify from what kind of color a cat is, or you can find out which breed of dog you're seeing in this image, not just a cat or dog. So these neural networks can go as broad as possible. So so let's see what happens with the next layer. So that is activation layers, activation functions, in other words. So you have two functions here. So for getting started, these two functions would give a pretty good idea. One is sigmoid and one is ReLU. So the sigmoid, like, it is just a function. If a value is lying in this region, then it would return 0, and if anything is lying here, it would return 1. So that is how it works. And when you see ReLU, if any value is greater than or linearly more than this line, then it will return 1, otherwise it will be returning 0. So, or you can think of other words as max of 0 of x. So this is how ReLU works. I know that it might not make sense at this point of time, but in the future slides, you will get an understanding. To your question, we'll see why activation functions are used. So here we have a simple diagram here. So you have an input, any kind of bit, or like 1 or 0 or something. You have a function here, so we'll just check whether it is satisfying this function, and if it is satisfying, then we'll activate the neuron. So you can think of neuron as any kind of number. So that is it. And if it is not satisfying this function, it'll say no. So we'll see what these function might be. So here our input is 5, so the function we need to satisfy is it should be less than 10. So it is satisfying, that is when we'll be activating the neuron, and if it is not, we'll not be activating the neuron. So you might get the idea, why are we doing all of this? So for neural networks to learn different features, like if they have an edge, or if they have a particular value inside them, a particular color, these activation functions help you get to understand, like mission to understand these kind of features automatically. So the next example might be, here you have 7. So the function that we have here is whether it has a curve, and the answer is no. So because they have straight edges, so it's like it's not getting activated. So if you see the next example, we have 6. So it has a curve, right? So it has different curves. So that's why it is satisfied and it is activating a neuron. So what happens is, right now you're only seeing one neuron. So if you see like 10 or 20 neurons, that's where you're seeing, like mission to create its own rules about what these functions should be like. So so yeah, so when we look into here, there is something called weights and biases. So this is an actual example of how uh, neural network learns. So here you have an image. So just like what we have seen before, you have different layers. So when you pass a particular image, it gets into this. These are called neurons. Okay, so before I was saying that activating a neuron, right? This particular element is this. Each one of them is a neuron. and you're connecting this image into different neurons and you're activating. So here it might check whether this particular image has a nose. So if it is having a nose, then it will send that yes to this another neuron. So these activation functions help you, like, kind of make sure a particular neuron is connecting to another neuron. So instead of connecting all the neurons to all the other neurons, here in this example you can see the thickness. Here you have different connections and all of them have the same thickness, but when you come here, the thickness changes because this particular neuron is getting connected to this neuron very good. So that is why you have a strong bond between these two neurons. And similarly, when you look into this neuron and this neuron, you might not see that thickness or that strong bond. So the bond is decided by activation functions. Like, these are the activation functions. So did you understand, Amok? Like, why we use activation functions? If not, we can get into the depth, like why it's happening. And later on you can see this neuron gets activated and it is giving strong signal to this particular label. It is activating this. If the same, this labrador is getting activated by these two neurons more. Even other neurons have an impact on this label or the class, but majority of the strong connection comes from these two neurons because of different functions inside them. Okay, so you understand?
So
Hmm?
the okay after giving the input that you have shown us here about a dog and a cat,
Mm-hmm.
activation function works on those things and differentiates them into different neurons, and
Yeah.
for what we are searching it, it makes a stronger bond with another neuron so that you can label it or classify them into one type or another type. That's what
Yes.
you're saying, right?
Yes, yes. You're activating. Yes, that is exactly correct. So, like, in the beginning, as you can see, every connection gets equal importance. But, like, this particular neuron will be talking about plants or different kind of other colors. So here, if you see, this doesn't have white color, but if this neuron is talking about white color, then this entire connection would be zero, because there is no connection between this white color neuron and this image. So in this particular neuron, you can see here it is having green color. So because of green color, it is getting activated and it is sending it to other neurons. It's like if it is satisfying some kind of like inner rules, it will be activated. So these inner rules and why, like, at this point of time you might not get why we are talking about activation functions and very in depth, but as we move on to the other slides, you might get hands-on experience about what these neurons are and what these activation functions are. So at this point of time you just need to have these keywords that this is a neural network, this is how the neural network looks, this is a for a visualization, this is how it looks. But when you are implementing it, it would be more of a formula based one. So in this particular example we have only two layers, but like larger networks you have 10s or 20 different layers. So and number of neurons might increase. So as this is a small example, we have less number of neurons in each layer. So this is the input layer, this is an output layer, and these are the labels. Okay, so this sort of image classification. So this is a simple example of image classification. We use neural networks in order to solve complicated tasks. So at this point of time, you can relate neural networks to solving complicated tasks, which you can't do it with simple rules. So you can try out these two modules inside Crowdsource application, and it will give you better perspective into how, like, what are these doing, like if you have it in real life prediction. So if you have your mobile, try these things out, and till then we'll have other session. So we'll have 2 minutes break right now, and we'll continue with other half. So by the time you can get into this. And if anybody has any doubt, you can ask us right now. And it would be great even if you can share any kind of experience that you have encountered when you're using this application. So it'll be helpful for others. Okay.
I used this image label verification yesterday and
Okay.
today morning too, but what I saw, I chose that board option. I mean,
Okay.
uh,
Mm-hmm.
that board option, and it used to give me all the different kinds of pictures, like board on buildings and beaches, on
Okay.
side roads, and somewhere in
Okay.
between people.
Mm-hmm.
All those things were there, but yeah, just now I did not like literally understand. I thought like I was teaching it, but at the same time now I understood that that was actually an activation function which you're using there. So if it is in between people, it used to like the question was where is the board, right? So
Yeah,
in
yeah.
between people, the in where is the board means that's the activation function that you're talking about. And
Yes, like at this point of time, here you see, right? This is just to explain why, like how activation functions exist. But when you get into the neural networks, they are more of abstract functions. So they learn to write down these new rules. Like we can't write whether an image has green or blue, right? So what this entire network does is, based on the output, it'll try to learn whether it did anything wrong. So it'll try to update its neuron. So it'll try to give more importance to the features that exist. Like, humans can easily find out that edges exist, right, in a dog, but machine finds very difficult. So that's where we have this large, complicated networks in between to find out these complicated stuff. And it is really good that you're getting that hands-on thing. So when you try it out, it feels like magic, but when you get into the deep learning implementation, it is kind of very interesting topic. Thanks, Amol, for sharing your experience. And my friend Sneha would continue from here, talking about in more in depth about hidden layers and practical implementation of this. So hands-on workshop.
So far you've basically learned a little bit about what a neuron is. You know that a neuron is basically the unit structure of a large neural network. What does this neural network do exactly? It basically learns information and it helps you accomplish a variety of tasks. I'm sure there are still so many questions in your mind. Why are there? I'm sure when you saw the first few images, you were thinking, why are there only 3 layers or 2 layers? What if you add a layer or remove a layer? What if there's an extra neuron or you remove a neuron in a particular layer? Then what happens? So, to put all these questions to rest, what we must do is try some hands on with neural networks. So, the image I have in front of me is basically called the Tensorflow Playground. I'll be sharing the link shortly. So what is this TensorFlow Playground exactly? If you look at the image on your screen right now, it does look like a neural network that Nikhilesh was showing in the previous slides, right? It has, let's say, an input, it has some hidden layers, and it's giving you some output. So this is the TensorFlow Playground. Basically, without any code or mathematics, it just allows you to try and test neurons just to understand how it works, what goes on behind it, and like to give you an overview of what the working of a neural network looks like. So first, we have the output side. And in the output, you can see certain terms like test loss, training loss, you have this figure, and certain other things. With this, what are we trying to do with this? So you can see here there are orange dots and there are blue dots. So the task here is basically to separate the orange dots from the blue dots. So if you think of this, it's basically mathematically modeling classification. You can think of the orange dots as one class, and then you can think of the blue dots as another class. And what we're trying to do here in this particular TensorFlow Playground is that we're trying to use different ways in which we can draw a boundary that separates the orange dots from the blue dots. Now, a test loss and a training loss. Okay, now you've heard the word test loss and training loss, or perhaps for the first time you're looking at it on this screen. Could you maybe hypothesize or tell me what do you think a test loss or a training loss could be? Anyone? It's okay if it's wrong, but anything. What do you possibly think it could be?
Test loss could be like it failed to recognize that this is orange and this is blue dot. And training losses, we failed to teach the neurons how to behave.
Okay,
Right.
so that was not completely correct, but I'm really glad that you're on the right track. So good job, Amok. So let me just tell you exactly what a test loss and a training loss is. Now, if you remember from the previous session, a stage of ML has 3 steps. So one is data, one is modeling, and the other is production. So in the modeling phase, that is the main phase where the machine learning model learns from the data, learns patterns, learns features from the data, and is able to perform the particular task. So in that particular phase with our data, what did we do? We split it into 3 different sets. One was the training set, one was the validation set, and one was the testing set. So I said the training set is basically like sending the model to school. Validation set is like basically studying before an exam. And the test set is basically a final exam. So here they've combined both training and validation together, and they also have testing. So there is no separate validation set here. So in the training loss, what does that mean? That means that when the model is learning, what kind of mistakes does it make? Think of it in this scenario. Right before an exam, you will be looking at some resources, previous year question papers, your class notes, and you'll probably like cover the answer and try to answer it on your own. So the the model also is doing the same thing with the data. It's basically looking at the data that it already has, and it tries its best to classify it correctly. So the number of mistakes it makes there, that is the training loss. So loss essentially is the difference between the observed output, that is the output that we want, and the predicted output, that is the output that the model predicted, which is seeing how wrong or how much difference is there between the actual and the predicted value. That is the training loss. Now, test loss is like the final exam, that is how well the model performs on completely unseen data. So there will be unseen data that's given to the model during its testing phase. So the loss there, that is the difference between the actual and the predicted value in the testing phase, that is known as the test loss. So that's the difference between the training and the test loss over here. And our objective is basically to draw a boundary between these two. So that's about the output layer. Now let's move on to the features. Now features, as the name says, it is basically what properties do you want to feed in based on what do you want the model to learn from. So you can think of this as the input that's given to this neural network. Then we have hidden layers. So there's normally an input. There are usually in a neural network architecture, there are usually hidden layers. So what are these hidden layers and why are they there? Hidden layers basically help you learn better. That is, now you have, if you just have this, that means you just have two neurons to learn all this and to predict the boundary of like what separates the yellow dots from the orange and the blue dots. But when you have a hidden layer, what happens? You have these many extra neurons to aid you to learn the features of that model, to learn how it's being separated, and then to help you further give you a boundary. So that's what the hidden layers do. Right? So this is the exercise and we'll get started with our tasks. All right. Let's get started. So maybe I would give you a couple of minutes, right? Just play around with this. Just start running this and you can change this. I know you may not know what the meaning of all of this is, but just try playing around with it and let me know what you observe. Maybe increase this, decrease this, change this thing called activation, try adding more hidden layers, more neurons, and let me know anything that you observe. I'll give you a couple of minutes. All right, we'll just proceed ahead. So this is basically a playground. Now let's get started. And as you can see, this is how you start running. So this means that the model starts training. And then you have your epochs here. Epochs, if you think of it in the general sense, it means that the number of times the whole, basically a model has run over the entire data. That is an epoch. I will get to this in a bit. So let's start with our first task. Okay. The model given the model as given combines our two input features into a single neuron. Will this model learn any non-linearities? Run it to confirm your guess. Can anyone let me know? Will this model learn any non-linearities? All right. Did anyone?
It doesn't learn non-linearities.
Great. Correct. Exactly. And why is that? Well, Amog, do you have any answer as to why it is? Whatever you think, it's okay if it's wrong.
I'm just guessing it because whichever if the data itself is wrong, how can there be non-linearity in it? I mean, how can there be linearity in it? So it cannot learn non-linearities because the data itself is wrong.
Okay, that was a good attempt, but that is not the correct answer. But really good job, Amok, for answering all this. So basically, look at this data. What is your aim here? Your aim is to separate the orange dots and the blue dots. Just one question. Can any straight line separate? Can any straight line very clearly separate the orange and the blue dots? Just one line. Can you perhaps draw a straight line that could very correctly, or at least most correctly, just separate the orange and the blue dots? Is that possible?
No, it's not possible.
It's not possible, right? So that's not possible. So that means that the boundary that separates the orange and the blue dots here is non-linear. That means that a single straight line cannot separate the blue dots and the yellow dots. So now if you actually come back here and look at activation, activation is set to linear. That means that it can only learn the linear information. It treats this data as a linear classification problem. That means that there is a single straight line that can classify the blue dots from the orange dots. Now, as we learned in the previous session, that there are activation functions that are non-linear. For example, ReLU. What does ReLU do? When the value of a neuron is greater than 0, then ReLU assigns that value. And if it's less than 0, then ReLU gives you the value of 0. So ReLU stands for rectified linear unit. So now maybe try changing this from linear to ReLU. You can leave the others as is and start running again. Is it still separating the orange dots from the blue dots? So you can see here, it's run so many times and it's still not separating the orange dots from the blue dots clearly. So that could possibly mean that we're not giving it enough place to train. So if you see here, when you just hover over this, you can see that the model is just trained on this one particular part. That means that it requires a few more neurons for it to train. So maybe let's try adding another hidden layer with 2 neurons and this also with 2 neurons, and let's try again. Is it able to classify it better? Right? What if we add another neuron here? So if there's any, so again, the neurons that I'm adding here, the hidden layers that I'm adding, this is all non-deterministic. So if you actually run this, is it able to classify the orange and the blue dots now? Like there are some mistakes, but is it able to overall?
Better than before.
Better than before, yeah. So I just added a few more layers and a few more neurons so that it can learn the features of this model better and basically help us come up with a boundary to separate the orange dots from the blue dots. Now, you may ask, how did you know that it required exactly 2 hidden layers, 3 neurons in one layer and 2 neurons in the other? No, I didn't know that. I was just simply doing trial and error. I was in fact doing that in front of you as well. So this process in actual artificial neural networks, even if you perhaps sit down to code it out, this is still a trial and error process. For you to, maybe you may have a neural network and that may not work. Maybe you'll start adding layers, start adding some more neurons, maybe removing some neurons, and then it starts working. So the way the model learns is non-deterministic. So that is not something, you know for sure that, okay, if you keep on adding layers, it'll do better. Actually, if you keep on adding layers, one, what you're doing is that you're making the problem way too complex. And two, it takes up a lot of your computation power. So we don't know what the optimal rate is. It's just something that we'll always have to use trial and error to get. So this, I think, comprised of task 1 and 2. So what we did, first we understood that since the activation function was linear, that is, the model was not able to learn any non-linearities. It was not able to separate the data in non-linear boundaries because we set the activation function as linear. It's only learning linear things. So activation function linear in the sense that what's the equation of line? Y equal to mx plus c. That is all that this was learning. But ReLU, it's a non-linear function. So now we're helping the model learn non-linearities. That's why we're changing the activation function from linear to ReLU. But still, the model was not able to learn when we had just 2 features and 1 neuron. That's because we did not give the model enough processing power for it to learn. And then once we increased some hidden layers and added some neurons, it started learning better. Now, if you actually see, you can see when you hover over the neuron, you can see what it's learning. So it's learning this here, this part here, and this is white. That means that's not learning anything. So you can actually remove this. And then it's learning this here and various things like that. All right. So try increasing the number of neurons in the hidden layer from 2 to 3 using the non-linear activation like ReLU. Can it model the data effectively? So let's try that. Okay, so this is just things that you can continue trying. So now I have these 3. Let's see how it runs with this. So for Amog, with 3, it worked better. But for me, the one that had two hidden layers, that worked better for me. So like I said, there is no correct or optimal answer. It's just things that you keep trying and testing, and you will perhaps reach a final conclusion that works well for you. All right. Now another thing is that you keep running it. Oh, see, it's working better now. So what you do is you keep running it until you get to low value on the training and the test loss. So what does this mean? This means that the model has kind of learned all that it can. And this is how it's classifying it now. Like the model has reached the ultimate level of learning. And it's tried various things, tried patterns, and now this is all it can learn. So you hope to definitely achieve a low training loss and a low test loss. So Amok, when you had that whole, when you said with 4 hidden layers it was not working well, and with 3 it was working well, did you happen to notice your training loss and test loss?
Yeah, it was a bit more there.
Okay, was the training loss higher than the test loss, or how was it?
Yeah, no, the test was more than the training loss.
Okay, so that means that it's not performing that great on unseen data. So that's what test loss being high means. All right, let's continue. So again, what they're trying to say here is that just continue experimenting as and how you can. Add more layers, remove more layers, and try to see if they can get a test loss of 0.177 or lower. So maybe try with 3 hidden layers and then maybe have 3 neurons per layer, or 3 neurons in one layer and 2 neurons in the others, or things like that. So just try your own architectures and see what works and gives you a loss of less than 0.177. All right, we'll move on. And you can check these answers. But again, this was done by the person who actually worked on this. So your answers may be different from what the answers here are, and that's perfectly fine. Okay, so again, we have the same data. Now, what are they saying here? Run the model 4 or 5 times. Before each trial, hit the reset network button to get a random initialization. So let each trial run for at least 500 steps to ensure convergence. So I'll explain what convergence is. So basically, now there's something here known as the learning rate. So what's a learning rate? Think of it in this way. What's our learning rate? Our learning rate is that we first start in our pre-primary, then we go to first standard, then we go to second standard, then third standard, like that till 12th, then college. So we go in this, we don't learn everything at once, right? We go in this step-by-step manner. That's how a neural network also learns. It goes in a step-by-step manner and it wants to converge. I'm not going into the mathematics of it because I don't want to confuse you, but you can think of converge as maybe reach the lowest possible loss. That's what you can think of converge as. So the learning rate that you take here must be optimal. It shouldn't be too high. So if it's too high, then, I mean, think of it this way. After first standard, you don't directly go to the third standard. That way, you will not really learn anything. You'll miss out on a lot of things, and your learning will just degrade from there because you didn't understand some concepts from your second standard. So you always go first standard, second standard, and third standard. And it's not the case that even if you did well in first standard, you stay there for 2 years. You go in that optimal pace. So don't set the learning rate as too low or too high, because that either way the model won't be learning much. 0.01 I think is optimal here. So what here you can try and do is start running the model and then see how it works, and then maybe reset it, like let it run for 500 epochs, and then what you do is reset it and try running it again. So if you saw in my screen as well, when I first ran it, the boundary was different. When I ran it again, the boundary was again different. Did that happen with any of you, or did you all get the same looking boundaries?
Yeah, the boundaries changed.
The boundaries kept changing, right? Like after the first time it reached some other final answer, and then again it reached some other final answer. Now why is that? That's because when you're resetting this, your initialization changes. So when your initialization changes, what happens is that the initial parameters of the model now completely changes. So maybe with your first try, the model worked very well because initialization was done well. With your second try, maybe the initialization was a bit off. So the boundary detection was also a bit off. So when you reset it, the initialization changes and it's quite random. You never know when you get the actual or correct answer. So you can try and experiment that. And you can try making the model slightly more complex by adding a layer or a couple of extra nodes. So you can add an extra layer and then maybe try it again. So it was kind of able to classify here. Although it took in some blue dots into its boundary, it was able to classify here. Did adding a layer work better for anyone, or did the first just, having one layer do?
Adding layers helped for mine.
Adding layers helped for yours. That's nice. That's nice. So how many layers did yours have?
3 hidden layers.
3 hidden layers. Okay, and that worked the best for you.
Yeah.
That's nice. So like I said, this is non-deterministic. So maybe 3 layers may not work well for me because perhaps my initialization was set to a different rate. All right, so that's about this exercise. So I guess you've got a small understanding of what a hidden layer is. A hidden layer basically helps you learn more about the model. In each layer, there are different neurons, and these neurons basically help you understand different features of the model to accomplish the final task. And a final task here is to separate the blue dots from the orange dots. So that's about this. So we tried different initializations. So as you keep resetting the model, you don't always get the same boundary. Why is that? Because with this TensorFlow Playground, every time you reset the model, the initialization changes. So this shows that the initialization plays a very, very crucial role in finding the boundary or finding, basically accomplishing your task. So when you're actually coding out a neural network in this manner, you're not going to have different initializations each time. You will have the similar or one set of initializations when you start running your model. So that time you can keep, trying to change the initialization from this value to that value, and you'll understand, you'll finally reach one optimal value and you can proceed ahead from there. So that setting out the initialization, that is also a trial and error process. So there is a lot of trial and error involved, be it how many neurons you require, be it how many hidden layers are there, be it the initialization that you set. So yeah, by the way, when I was talking about initialization, I mean for this. So your initialization could be set to 0, and then your learning rate starts from 0, or your initialization could be set to 2, and a learning rate starts from 2. So it goes from 2 plus, it goes in that manner. So not plus exactly, but that's a mathematical equation I won't get into. And all this comprises under an algorithm called gradient descent. So if you're interested, you can check it out later, but I will not be talking about it because there is a little bit of math involved and I don't want to confuse you today. So yeah, so that is what I meant by initialization when I kept saying. So initialization is which number does your gradient descent algorithm start, or what is the initial value of your gradient descent algorithm? So when you're actually coding it out, you will try and test it on a number of values, and then you will finally find out that maybe 0.1 works for you. So you'll model your neural network with that value. So initialization plays a very important role, and you understood that it's not always the fact that as you keep increasing the layers, it's not you get better performance. Sometimes as you increase the layers exponentially, then it actually performs worse than it's supposed to. All right, and then we'll just finish these 2 tasks, and then I'll be showing you another really cool and interesting machine that's that I'm sure you'll be interested in. So now we have this spiral data. So what is this task? Train the best model you can just using these 2 features. So you can try changing everything, and okay, I made some changes to it. So train with just this much, these 2 features and this layer, just try training the model. So let's try. So you can see that it's absolutely not differentiating the the orange dots from the blue dots. It's not learning anything at all. That's because it's learning only this much and this much. Sometimes you need to do something known as feature engineering, which means that you need to involve different types of features. So let's say you want to find maybe how much time it takes a man from, let's say, point A to point B. And with you have speed and you have distance. But the actual value that will help you indicate this is time. So you need to do feature engineering. That means that, do some mathematical equations on a few features. So for example, if you had speed and distance, you would do speed divided by distance. So that's feature engineering. So that's how you do feature engineering. You either multiply a few features or you divide a few features and you get it that way. So now let's try doing some feature engineering. So when we just had these few features, it didn't really work well. Did it work well for anyone? Did anyone maybe try with just these 2 features? So I'm sure no one was able to exactly achieve the required boundary with just these 2 features. So now let's start doing things. Let's start doing feature engineering. That is, now this was x1 and x2. Feature engineering by doing x1 square. Let's add x2 square. Let's maybe do a feature cross of x1 and x2. And let's maybe also add these 2, the sine of x1 and sine of x2. It's still not working that great, but it's definitely better than the previous one, right? Did anyone get a better model when you added a few more features? Or did you get a perfect spiral? Sorry?
Kind of differentiating where is the colors, but not that great, like you said.
Not that great. Okay, so maybe there may be some optimal value once you do trial and error. Amog, how many feature crosses, what were your features and how many hidden layers did you have?
I had 3 hidden layers, and in one I had 4 neurons, 2 neurons and 3 neurons.
Okay. Again, like I said, it amounts to a lot of trial and error. So we could maybe remove a couple and try again. It's not doing that well. The loss keeps fluctuating. It's not reached its convergence point yet. It just keeps fluctuating no matter how long the epochs go on. So definitely there will be a particular architecture that suffices this. So that, again, like I said, involves quite a bit of trial and error. So this was about the TensorFlow Playground. I hope you understood how neural network looks like, what a neuron learns, and the features that you give in, the things about hidden layers, test loss, training loss, and also some information about weights. So actually, I wanted to show you that. So when you start running this, do you see that this line is thin and then this line is thicker? And actually, if you hover over it, you see the weight here is 0.27. So that's low. And when you hover over this very thick line, you see that the weight is 0.95. Can anyone tell me what this means? All right.
Well,
So
it means that the thick line is given more importance, and the thin line is not that much looked into, like how
correct. Exactly. Very
it,
good. That is absolutely correct. So what does this mean? This means that this feature that has a very thick line, that means that its weight is high. That is, the weight given to this is high, which means that it's able to learn more features to get to get the optimal boundary. That is, it's a very valuable feature in our neural network. That's why it has higher weight, just like what Amog mentioned. So when there's a thicker line, that means that, like Amog mentioned, it's much more valuable to our neural network. It's learning well for us to classify it. So that's what a higher weight or a thicker line here means. All right. Then we shall continue to some very cool machine called the Teachable Machine. So we did these few tasks. Again, this link is with you, and we'll be sharing the slides with you. So you can again try these tasks and see why it works that way, why it doesn't. You can try researching some things on your own, and maybe let us know next time how you played around with this. All right, I'll just send this link. So should just take around 5 minutes and we'll be done. All right, so now let's look at this very, very cool machine called the Teachable Machine. So what we can do with this Teachable Machine is that we can teach our computers, there is a neural network behind this, and we can teach it to recognize images and things like that. So let's get started. And maybe I'll show you an example of an image project. So let's maybe teach this model to differentiate my hand that forms a stone, a paper, and a scissors. So I'll call the different classes that way. So I'll call it stone. I'll call this paper. I'll add another one. Scissors. All right. So let's try training some images. All right, then. And scissors. All right, so we have our 3 classes, stone, paper, and scissors. Now maybe let's train this model. It should take a little bit of time. You guys can also try your own, maybe different classes of your own. It could be just 1, 2, difference between 2 numbers or things like that. All right, now let's test this model. So if I hold this up, you can see that the maximum answer that's coming is stone. Just a second. Now if I hold this, it's still fluctuating between like paper and scissors, but it's mostly giving you the answer of paper. If I hold this, it's giving you scissors as the answer. Maybe I try it like this or something like this. It's still giving you scissors. If I type this again, so it's for some reason confusing a bit between paper and scissors, but it's still settling for paper. Now let's try if we can confuse this machine. So let me hold this. So this is a scissor. It's predicting this as a scissor, but it's not a scissor. What if I hold this? It's also predicting this as a scissor. What if I do this? Or what if I do this? Or this? So what is happening here? It's that we're showing it different data that basically was never used in the training process. So now it doesn't know what is happening. Like the 3 classes that we gave it was stone, paper, and scissors. But now when I was showing things like 6 or when I was showing 1 and things like that, it was basically different from what we trained it on. So the machine was constantly getting confused. So this is one limitation of a neural network. It can get confused in this manner if you look at this, teachable network. Sorry, a teachable machine. It can get, when it comes to like completely a whole different class that you basically never trained it on, it can definitely get confused. So maybe you guys can also try this out. You don't have to use things with your hand. You can maybe show an image of a dog and then image of a cat, and then maybe try an image of a deer. So it'll try to give you the most optimal answer, but that won't be right because we never trained it on a deer. So that's all we have about this session today. Just a few questions to keep you in check, maybe. All right, if there are no other doubts, thank you so much for taking the time out to attend this session today. I hope you at least have a brief understanding of what a neural network is and how you can use the TensorFlow Playground to understand the workings of a neural network and, basically play around with it. So if you have any other doubts or questions, you can feel free to ask us right now. And if there is nothing, you may leave the call. The session has ended for today. Thank you so much.